Good evening, everyone. My name is Mr. Malu. I'm a lecturer at the UJ at UJ in Maths department, and I would like to thank my colleague Dr. Sibakodi for giving me this opportunity to give a sort of introduction topic to discuss with you all. So before we get started, let's first. I don't have any slides first of all. So what I'm going to do is that as I talk, I'm going to write on the blank screen that you see. So the first thing is that what is a linear algebra? A linear algebra consists of a lot of topics such as system of equations that you have seen in grade 12. Then we have matrices being a core topic in linear algebra. Then we have vectors, we got transformations, we have eigenvalues, eigenvectors. So there is many topics in linear algebra. However, my topic for today, what I want you guys to know is that what it means to be a metric. In other words, I want you guys to give you an introduction to a matrices, right? So let's look at that. Before we jump into matrices, let's just recall a few stuff from your grade 12 work. So if you guys recall from your grade 12, so recall from grade 12 that you're given a two system of equations such as, let's just say x plus y equals to 1, and then we say 2x plus y equals to 6. And the question here says solve for x and y in the above system. So in the given system above. Now, this is something that you have done in grade 12, which you call a simultaneous equation. Am I right? What we do, if you recall, I'm just going to give you a sort of guidelines how to solve this problem, is that we make one equation as a subject of the formula. And if you take this, if we name this equation number 1, we take this equation number 2, then we say, okay, I'll make y as a subject of the formula in equation number 1. Hence, I'm going to get y equals to 1 minus x, which I'm going to call equation number 3. And then now we say substitute equation number 3 into 2 to solve for this system, right? And this is what we're going to do in the later of the talk. Or what we're going to do is that we're going to see what happens when we have more equations and we have more variables. Now, if you imagine a case where we have something like this, 2x plus 3y plus z equals to 2, 2x plus 6y equals to 4, 4z equals to 9, minus x minus y minus z equals to 10. Now imagine doing all this manually as we did with two system of equations. It will take us a lot of time. There will be a lot of algebraic work that needs to be done. So in order to avoid this, tedious work that you have, we can use of a metric, which I'm going to show you how to do that. So that is all from grade 12, and I wanted to emphasize that we can always solve this using a matrices that we're going to learn in the later of the later of the talk. So before we look at, let's look at some definitions. Let's look at definition number 1. This definition has to do with linear equation. So what it means to be a linear equation, right? So a linear equation, since we talk about linear algebra, right? So we want to know what it means to be a linear, right? So a linear equation has the form of the following. So the linear equation has the form as follows: a1, x1, a2, x2 plus an xn equals to some k. I'm going to explain this to you. So now if you look at this, the AIs that you guys see, there are some numbers that are part of real numbers, okay? And the number k that you see as well is also a constant. So k is also some constant. And The x size that you guys see, we call that a variable. A variable. So it says a linear equation. So if I want to say whether the given equation is a linear or not, what you need to check is as follows. It has the form of a constant a1, x1, a2, x2, up to an xn. Now, what is important to be a linear, if you look at the power of your variables, this is what is important here. All this x size, which we call a variable, the power of this variable has to be 1. If the power of this variable is 1, such a system, such an equation, we call it a linear equation. All right, so let us look at some examples here to identify which of the following. So identify which of the following are linear equations. Okay, let's look at this exercise. So I'm going to give you guys, let's look at example number 1. 2x plus 3y equals to 6. And my question to you is this a linear equation or not? Is this a linear equation or not? Let's pause for a second and let us think whether this given equation is a linear or not, okay? As keep in mind, we said that in order for you to have a linear equation form, what you need to check is that make sure that the variable that you have in your equation has a power 1, right? So now let us look at in our case, we got two variables, right? We have variable x, we have variable y. What is the power of x? So the power of x is equals to 1. You all agree with me? So the power of x is equals to 1. Then the power of variable y, in other words, the exponent, the power of y is also equals to 1. So now if you look at this equation, it does satisfy this form that we saw early on the top here, that we have two variables, both of them have power of the exponent 1, together with some constants, which is 2 in this case and 3 in this case with y, which is equal to some constant k. Hence, we would say that this equation, this equation is a linear equation. Any questions? Hence, this equation is a linear equation. All right. Let us look at some more examples on this before I move on, whether to identify which given equations are linear and which one are not linear, right? So let's look at 2 or 3 more examples. Let's see if I give you guys sine x plus 2y equals to 6. And my question to you now again is the same question. Is this equation a linear or not? So is this equation linear or not? Let us think. As I said, in order for you to be a linear equation, right? We said the linear equation has the form of this. It has a form of a1, a2, up to xn. So remember your variable, right? Which we have xi's. The variable has to have an exponent 1 or the power 1 together with some constant, right? I mean, the ai's, some ai's can be 0. It's not a big deal, but it has to multiply by some constant equals to other constant k, right? Now let's look at in our case. In our case, y here, it is a variable, right? Y is a variable. What's the power of y? Is 1. The power of y here is 1. We also have some constant k. If you resemble this with the definition, this is our constant k, which is equals to 6. However, the problem is that if you look at this guy, the x, right? Remember, the x here is not a variable, right? This is a function now. We have a function sine of x. Am I right? It's no longer a variable, okay? So therefore, because of this guy, we say that since x is not a variable in this and plus in particular is not a, it does not even have a power 1. So since x is not a variable here, therefore we conclude that since sine x is a function which is not linear, right? So therefore we say that therefore this example, this equation here, therefore the given equation is not linear. Okay. Let us look at the last example before I go on. And example number 3, let's see if you guys can catch this. I'll give you guys just a few seconds to try to figure out on your own and see if you can follow what I'm trying to emphasize in this definition. So let's say you have pi x plus 2y equals to 3. And it's the same question. Is this a linear equation or not? Is this a linear equation or not? Right? Let's pause for a second here. And I want you guys to think just for a few minutes and see if you guys can figure out whether this equation is linear or not. Okay, I'll just wait for a few seconds and then I'll tell you guys the answer. All right, so the answer here has to be that it's not a linear equation. Am I right? Oh, just kidding, right? This equation is linear. Why? Because if you look at in this equation, the x here, right? It's a variable and it has power 1, right? So in this case, the exponent of x is 1, right? And also the exponent of y is 1 together with some constant, right? Remember, pi is a number, right? Pi is approximately is 3 point something something, right? It's 3.21 something something. So pi is a number which multiplied by x, so hence x is a variable where the power is 1, right? Plus in the second term we have y, which is also a variable. It has an exponent 1 together with multiplied by some constant which is 2, and we say this is equals to some constant k which is 3 in this case. So therefore in this case this guy is a linear equation. Okay, it is a linear equation. Let us look at the last example here, number 4. Pi x squared plus 2y equals to 3. Now, is this a linear equation or not? And I'm assuming that now I think you guys used to the concept of being a linear equation. You can step forward, say that this is not a linear equation. Why? Can one think why this is not a linear equation? So this won't be a linear equation. It's because if you look at the power of x, right? What is the exponent of x in this case? X is a variable, yes, but the exponent of x, the exponent of x, it's 2 and not 1, right? And therefore, we say that therefore this is not a linear equation, right? And remember, when we talk about linear equations, we normally talk about straight lines, right? Because if you look at so this is all how to identify a linear equation and not. Okay, so given equation, we can always identify whether that equation is linear or not. And the only thing you need to check is that what variables it has. Let's say if it has x, y, z variables, then you need to check what is the exponent of those variables. If the exponent of those all variables are 1 and it is multiplied by some constant equals to some constant k, then we say that this equation, it is a linear equation, right? However, if you have at least one variable where the power is not 1, the exponent is not 1, then we say it's not a linear equation, right? Or if it's a combination of some functions, or if we go back to example number 2, where we had sine x plus 2y, it's also not a linear equation because sine x is not linear, it's a function, right? So now, let us see. So when we talk about linear equations, I want to just I want you guys to emphasize that if you recall, when you talk about linear equation of form ax plus by equals to c, if you recall this, this is an equation of a straight line, right? If I make y the subject of the formula, I would get that this would be minus ax plus c over b, right? Which can be written as, if you recall, this is the familiar form that you're all used to, where big C is some constant, which is a combination of that, and then A over B is equals to your gradient M that you guys used to the standard equation from grade 12. So which means that whenever you see an equation of form ax plus by equals to c, we actually talking about straight lines, okay? That's what we're talking about, okay? So I'm hoping that now you guys understood what it means to be a linear equations, okay? And you guys also and I hope you understood that this is a geometrical representation of a linear, of this linear. In particular, here we're looking at a 2D system, right? This is x and y coordinate 2D plane. So therefore, this is a straight line. If we're in a 3D plane, then if we're in a three coordinate system, then we have a plane, sort of like a paper sheet, you know. I'll draw it for you guys a bit later there. Now, let's look at, before I show you guys matrices as well, let's look at system of equations. Okay. So now, let's just pretend that you're given a two equations, right? As we discussed earlier, let me think if I short, okay, let me talk about that. Yes, okay. So let's just say you're given two lines. You're looking at ax plus by equals to c, and I'm going to call this straight line number one, right? Remember, this equation, as I said earlier, represent a straight line equation. So I'm going to call that line one, and let us just see that we have dx plus ey equals to f. And I'm going to call this equation of straight line two, okay? And my question to you, my question would be now is that one can ask, what are the possibles? What are the possible solutions? Possible solutions to this type of a system equation, to this given system of equations. Remember, in this system, the one that we're considering here, and let me just give you a definition of system of equation. When I'm talking about system of equations, what I mean is that is the finite collection of these linear equations. So in other words, what we're trying to do here is that you want to solve for x and y simultaneously, and we call that a system of equations, okay? I'm going to explain this real quick using a geometrical representation, right? So remember, in this case, what are we given? We just given two lines, am I right? We given line one, line two. So now remember, these are the possible cases that can happen. Is that if line one and line two, so I'm going to call this L1, line one and line two. Now remember, we can see from the sketch, right? If line one and line two are parallel, we all know what it means to be a parallel, right? A parallel is a line that never touches and it follows the trajectory, right? So, and it follows this distance, it maintains the distance between them as well, right? So it means that if line one and line two are parallel, right, then we say that that system will have no solutions. Am I right? Do you all see that? Why? Why would this system will have no solutions? Because if you want to solve for x and y, we can clearly see from the geometrical representation of line one and line two that they're never going to touch. So if they're not touching, if there is no point of intersection, therefore there is no solutions, right, in this case. The second scenario that we can have is where now two lines meet, right? Two straight lines meet at some point. In other words, we do now have a point of intersections. And now remember, for two straight lines, you're always going to have only one point of intersection. So in this scenario, we do have a solution, okay? And in particular, we have exactly one solution. Right. So I'm trying to explain this concept of system of equations. Also, we're going to look at three equations, 4 equations later on. But for now, I want to introduce want to start with the basics, right? So if you understand what's happening with 2D coordinate system, then you'll be able to grasp the content for the 3D system, right? So if you look at this, as we spoke earlier here, we have line 1 and line 2. So the first scenario we had is where the two lines are parallel. In other words, they're not touching. So therefore, there is no solutions. Number 2 is where two lines intersect. And now remember, you have only two straight lines, and hence there will only be one point of intersection. So therefore, it will have exactly one solution. But there is one more possibility that I'm sure you guys never thought about that. And that possibility would be then, let's just pretend that we have line 1 like this, okay? And then we have line 2. I'm going to change my color. But that line 2 basically sits on line 1. So in other words, the line 1 and line 2, so this would be orange color would be line 2. So now in this one, line 1 and line 2 coincide, right? So in other words, they are on top of each other, right? And how is that possible? So let me give you a quick algebraic form of that. So let's just say you have 2x plus 3y equals to 6. And if I just multiply this equation by, 1 by 3, so if I do that, then I have 6x, sorry. If I multiply by 3, then I would have 6x plus 9y equals to 18. Now recall, you can verify when you get time that these both lines, they will have same gradients, same intercepts, and it will have the same, basically it will have the same shape. In other words, it will just gonna sit on top of one another. And if that happens, then we have infinitely many solutions, right? We have infinitely many solutions. And why would that happen? As you can see from the geometrical representation, at each, as the moment I put my pointer, right, we can clearly see. Let me just change my color. The moment I put a pointer here, we get a solution. I put a pointer here, we get a solution. I put a pointer here, we get a solution. I put a pointer here, we get solutions. And remember, this line goes to infinity in both directions. Am I right? In actually all the directions goes to infinity, right? So therefore, whenever you see the two lines, in particular, we talk about 2D system here. So if two lines coincide, then we have infinitely many solutions. All right. So that's all from the system of equations. Now let me get to the topic that you guys, I'm sure you're all waiting for. It's to hear about matrices. What are matrices? What it means to be a metric, and so on and so forth. Okay. So first of all, a metric. What is a metric? Right? And when I talk about metric, right, I don't mean the movie that you guys seen in the, I don't know which year, in some 2000s year, there was a movie Metric. I'm not talking about that, right? How it does use some sort of idea there about the pixels, which I'm going to explain to you later. But when we talk about metric, it's a rectangular array. So a metric is a rectangular array. Rectangular array. It's a rectangular array of numbers. Okay. What I mean by that, I'm going to just show you guys that in a few seconds. And it is made up of some numbers in it, which we call entries. All right. And it also represented by columns and rows. So we're going to talk about that just in a second. So let's look at this. Recall this. Let's consider this system of equation. 2x plus y equals to 6, and then x plus y equals to 4. Now, what we're going to do is that, as I said, this is easy to solve. If you want to solve this simultaneously, I'm sure you can all do it, right? But why we need to know about matrices is that when we want to do this thing manually, obviously there's computers, if you have more equations, more variables, the computer can always do it for you. But let's say if you want to do it manually, and if you don't want to, if you have 3 or 4 system of equations, you don't want to waste time doing algebraically, right? So this is where we're going to use a concept of matrices. So this is what we're going to do, right? What the metric do is that since it says it's a rectangular array, so let's just put a sort of like a rectangle here. I'm not going to do the full rectangle, sort of like a brackets, and just pretend that it is sort of like a rectangle here. Just pretend this is a rectangle. Okay. And what we have here, in order to represent this in a form of a metric, is that we have to have the rows. So in a metric, I'm going to write it here. In a row, the number of rows is equal to number of equations. Let me first make this note here for you guys. So the number of rows in a metric is equals to the number of equations that you have. All right, number of equations that you're given, and then the number of columns in a metric. So number of columns in a metric is equals to the number of variables, number of known variables that you have, plus 1, and this plus 1. I'm going to represent the, okay, I'm going to tell you guys that a bit later. So okay, let's just say, okay, I'm just going to say plus 1 for augmented matrix. So plus 1. This is when we talk about the augmented. So what we're going to do now is something called augmented matrix of a given system. So let's pretend that you're given this system, right? You're given this and they ask you to now write this in a form of a metric. So first of all, let us ask ourselves a question. How many equations do we have? We have, as you can see, we have equation number 1, equation number 2, and because of that, we're going to have 2 rows, right? So I'm just going to use a different color just so that you guys know the difference here. That now, this would be row 1, and this would be row 2. Since we have 2 equations, we're going to have 2 rows for that in a metric. Let us ask ourselves questions. How many variables do we have? We got 2 variables, as you guys can see. We have variable x, variable y, and plus we need to add. Therefore, as you can see, this plus 1, this is an augmented metric. This plus 1 is for this solution that we have. Is this constant that you were given, right? So I'm going to represent this is the variable x, variable y, and this guys that you see, I'm going to say that represent that constant k that we have seen earlier, right? Now let us see. So a metric, right? In a metric, what is inside the metric? Inside the metric, you only, I mean, in your case, obviously, it only has real numbers, right? If we talk about numbers, we want to put the entries inside the metric, right? So my question to you now, the way we do this is that because we talk about row 1 now, it means we should go to equation number 1. Okay, let's go to equation number 1. Now remember, equation number 1 is 2x plus y equals to 6. Okay. What is the coefficient of x in equation number 1? Can you guys see the equation? The coefficient of x in equation number 1 is 2. So then we should put 2 here. Are you all fine with that? What is the coefficient of y in equation number 1? Remember, this is equation number 1. As you can see, the coefficient here is 1, right? So therefore, we're going to put a 1 here. And now I'm just going to draw this dotted line just to differentiate the columns as well. Remember, we have 3 columns, and so normally they partition the solution column by this dotted lines. Let me not just do that. I don't want you guys to confuse. Obviously, after this, we're going to do it much more efficiently. I'm doing this dotted line so that you guys just understand what we're doing. And then the value k, in other words, the constant in equation number 1 was 6, so we put 6 there. Okay. All right. Let us look at equation number 2 then. Equation number 2 is x plus y equals to 4. So what is the coefficient of x in equation number 2, guys? It's 1. So now we put that 1 in row 2. As I said, the rows represent the number of equations, right? Then if you look at the y here as well now, the coefficient of y here is 1. So we put 1 there. And now the constant k in equation number 2 is 4. So we put 4 there. So basically what we did now is that we converted this system of equations, this given system of equation into this metric, 2, 1, 6, 1, 1, 4. X and y. So you don't really need to write the x and y's on the top here, but I'm just writing it here so that you guys understand that this x, the first column that you see, it represents the coefficient of x in the equation number 1 and equation number 2. Then the second column that you see, so this is column 1. Remember, columns are vertical lines, right? So the columns, I know it is easy concept, but it is easy to get confused. I used to get confused a lot when I was introduced to this topic. So when I'm talking about columns, columns is a vertical lines. When I'm talking about rows, I'm talking about horizontal lines, right? So when we look at column 1, we have the coefficient of x in both equations. When you look at column 2, we have the coefficient of y's. And then when we look at column 3, we have the constants, given constants 6 and 4. Okay. So yeah, and we call this an augmented matrix. So why we call this an augmented matrix is now because we involving this case, right? We involving this given solutions of the constant k that was given. Since we're involving that, we call that augmented matrix. But let's just pretend that if you just write x and y, you don't want to do anything with the constants. You just write 2, 1, 1, and 1. And now we will call this a coefficient matrix. And you all see why the word coefficient here is because if you look at this array, this metric here, it's basically representing the coefficient of those system of equations. And we call that a coefficient matrix. All right, let's look at one more example. Let us look at one more example. X plus 2y plus z equals to 6 minus x plus z equals to 3. And then 2x minus 3y minus 4 or z equals to, let's just say 5. Okay, my question here now, let us convert this, right? Let us convert this into an augmented matrix, right? Now remember, as I said, the difference between augmented matrix. In an augmented matrix, you include the constants k that you given to a system of equations, okay? And in a coefficient matrix, we don't include that column, right? Now let us just see. I want you guys to tell me how many rows are we going to have? Let's just think. How many rows? And I'm talking about an augmented matrix, okay? As I said, in augmented matrix, you involve your given constants k. In other words, you do consider your 6, 3, and 5. So in augmented matrix, the last column should represent that. So augmented matrix, how many columns should we have? How many columns? And how many rows are we going to have? Can one thing about that? Let me recall. The number of rows would equals to the number of given equations. The number of columns would be equals to the number of variables that you given plus 1. The plus 1 is for this one here, the coefficient here, I mean the constant that you given to you. If you talk about coefficient matrix, then we don't consider this guy. We just take the x, y, and z. Okay. Now let me do this again here. We always use these brackets, right, to represent a metric. Okay, and what is inside this rectangular brackets that you see, we call that entries, and those entries are coming from this system of equations. Okay, so now let us look at this. In equation number 1, remember, I would say we're going to have row 1, row 2, and row 3, right? And then on the top, we're going to have x, we're going to have y, we're going to have z, and we're going to have a last column for k, right? The constant k, if you recall. Now, let's see. In row 1, guys, what is the coefficient of x? I mean, in other words, remember, row 1 represents equation number 1. So let me just name that for you guys here. This will be equation number 1, equation number 2, equation number 3. So now let's look at this one at a time. In equation number 1, what is the coefficient of x? What is the coefficient here of x? Let me change my color so that you guys see what happens here. What is the coefficient here with x? It's 1, right? So we're going to put a 1 there. What is the coefficient of y in equation number 1? As you guys can see, the coefficient with y is 2. So we put a 2 here. What is the coefficient of z here, guys? It's 1. So we put a 1 there. And then, as I said, always, whenever you're talking about augmented matrix, you want to separate your constant k, right? And therefore, we put this dotted line. It's not a must, but it's a good practice to have, so that you know that what is after this dotted line, we talk about variables, and what is after that, you talk about your given solution metric. In other words, your constant k. So in equation number 1, the constant k was given to us equals to 6. Okay. Are you all fine with the row 1 then? All right. Let us now look at row number 2. And in row number 2, what is the coefficient of x again here? let's see. The coefficient of x here it's a negative one, right? There's a negative sign. And there's one with that, so it will be a negative one. What is the coefficient of 0, guys, here? Do you guys see 0 in equation number 2? And as you can see, there is no 0, right? So hence, the coefficient then has to be 0, right? Because we can always just write this as 0y, right? Which means nothing. So therefore, in a place of y in equation number 2, we put a 0 because there is no y. Okay. What is there a z? Yes. In equation number 2, the coefficient of z is 1. So we put a 1 there. And the constant k is 3. So we put a 3 there. Okay. That would be for row 2. Let us look at the last one here. Now for row 3, we're going to consider equation number 3. So what is the coefficient of x in equation number 3 is 2. So we put a 2 there. What is the coefficient of y in equation number 3 is -3, so we put a -3. For z, we put a -4. And finally, the constant, which is 5. So I'm sure you all understand now what we mean when we talk about matrices, right? A matrices is just a basic, and remember this, it's just that we can represent a system of equation in form of a metric, and we can always go back as well, vice versa. So, and there's a lot of things going on in this matrix. Obviously, you're going to learn in your first year course, in your second and first year course, you're going to learn more about that. It's just a bit of introductions. I'm going to just give you guys an introduction of matrix, right? So this is a metric, right? A metric, as we said, is a rectangular array. Inside the metric, we have the entries, which we call the numbers, okay? In other words, real numbers. In your case, we're considering real numbers, okay? So therefore, this is an example of a metric as well. And as I say, since we're involving the constants k, we call this an augmented matrix. If I just draw the same metric like this now, just only with x, y, z, r1, r2, and remember the r1, and why I'm writing this so that you guys know we talk about equation 1, equation 2, equation 3. If I now just do this, -1, 0, 1, 2, -3, -4, then we call this a coefficient metric. A what? A coefficient metric, okay? And we can clearly see why we call this a coefficient metric now, because all those entries that you see, it represents the coefficient of that variable in that particular equation, okay? So you guys should be able to go back and forth. So in other words, you guys should be able to, from there to come here and from here to go back. Let's just look at a last example, a small one here quickly. So let's just see if I give you 3y equals to 1, minus x plus y equals to 3. Then let's represent this. Let's write an augmented matrix for this, right? An augmented matrix would be then row 1 for equation number 1, row 2 for equation number 2, x, y, and our constants k. So it will be 2, 3, -1, 1, 1, and 3. I'm sure that you guys all agree with that. Just have a look and then see. What I want you guys to do now is that let's see if I give you a metric in a following form. If I give you an augmented metric in particular, I'm not just going to talk about metric. Let's see if I give you an augmented metric. Because when I give you an augmented metric, I'm talking about system of equations as well. So x, y, this is a totally different example now. Z, together with constants k. I'll say 2, 3, 1, 1, 2, 4, 5. My question to you guys now, how do we go back? So how do we now write? Let's pretend that now this time you're given an augmented matrix. An augmented matrix. We're given this, and now how do we write a system of equations, right? The one way to do this, as I said, remember row 1 represent equation number 1. So now we have x. What is the coefficient of x in row 1 is 2. So we know in equation number 1, we have 2x. In equation number 1, again, we're going to have 0 y. Why? Because the coefficient of y in row 1 is 0. So therefore, we're going to have plus 0y. Now in row 1, in a column z, we have 1. So that would say we have plus z equals to constants 4. In a second equation now, row 2, we would have 3x because there's a 3, right? X in row 2. Then in column Y and row 2, we have 1. So it means there is Y plus 2Z equals to 5. So what I'm trying to emphasize here is that you guys should always able to go from augmented matrix to the system of equations and vice versa. You should be able to do that, okay? It's easy. Okay, now I'm going to, due to this time limit, I'm going to talk about just a few basic concepts, such as the dimension of a metric. All right, let's look at this. What is the dimension? Obviously, you guys might be wondering, okay, well, if you have a system of equations, right? We had this, and then we converted that into a metric. Now, question is, how do we solve this, right? How do we solve this to get the answers X, Y, and Z? And as I said, there is a way to do it. It's just that because of the time limit, I was not able to show you guys how to do that. But there is a way which you're going to learn in your first year and as well in your second year on how to solve this. But what we really focusing right now is just the basic introduction of matrices, okay? So now let's go to now what we mean by a dimension now, okay? A dimension of a metric. So a dimension of a metric is basically n is a n by m, where n represent number of rows and m represents, or let me just use the standard way of book where m and n, there's nothing wrong with that, m and n. So I'm going to say, so m represents the number of rows in the metric and n represents the number of columns, okay? Now let us look at some example, quick example here. Let's see if I give you a metric now. 2, 3, 1, 4, 2, 1. Can you guys tell me what is the dimension of this metric? What is the, or in other words, what is the size? Some people even call a size of a metric, or some call dimension. So what is the dimension of this given metric? Remember, I said the dimension is basically it's written as m times n. Okay, but remember, if we don't want to solve, we don't want to say, I'm going to see what's a common mistake that a lot of people do. Okay, so first of all, let us first identify. Remember, m represents the number of rows. So in our case, well, how many rows do we have? Remember, for rows we look at horizontal lines. For columns we look at vertical lines. So as you guys can see, we have, this is row 1, this is row 2. So we have 2 rows. Okay, what about columns? How many columns do we have? And if we talk about columns now, then as you guys can see, we have column 1, column 2, column 3. So this will be column 3. So therefore, the order, all right, as I said, the order, or some would prefer the size, or someone you will call it the dimension, depending on author or the lecturer that is going to lecture on this topic. So they use word order, size, dimension. So we call that the dimension of this metric, of this given metric, is basically the number of rows times it by number of columns, so which is 2 by 3, right? Remember, this time we read this as by. So it says 2 by 3, which means that we have 2 rows and 3 columns. So to the final answer to this is just simply 2 by 3. It's not equal to 6, right? I see a lot of the times when you ask the students what is the order, they would first write is 2 by 3, but they in back of their mind they're going to be thinking this notation as times, and they're going to say is equals to 6. But that's not the case, right? Whenever we talk about the dimension of a metric, it simply means it's the number of rows by number of columns. Okay, let's look at one more example on the order. If you now have 2 to that, can one of you tell me what is the order of this metric? What is the order? Right? Now the order here, as you guys can see, the rows, we have row number 1 and we have row number 2, right? So the m is equals to 2 rows, and n that represent columns is also 2 columns. So therefore, the order, remember the column here are also 2. As you guys can see, column number 1, column number 2. So therefore, the order of this metric, or the dimension of this metric, is 2 by 2, right? So whenever someone says that you're given a metric 2 by 2, what they what they're trying to emphasize is that you have 2 rows and 2 columns. If they say you are given a metric of dimension 5 by 6, what they mean by that you have 5 rows and 6 columns. Okay, am I clear? Let's say someone said given a metric A of dimension 5 by 6. What they mean by that in a metric you have 5 rows and you have 5 columns. Am I clear? Okay, that's what we mean by our order. Now we still have about 15 minutes, so let me just go show you guys some operations. Okay, so this is why the order was important, is because in order to define this operation, we need to know this order. Okay, and also keep in mind whenever it happens, right, that your number of rows is equal to the number of columns in a metric, right? So let me just write that for you. Whenever it happens that the number of rows equals to the number of columns in the metric, right? We call that metric, so we call that metric a square metric, or what? Or we call that a square metric, or square metric. We call that a square matrix. Okay, so whenever you see a word in a textbook or somewhere when you read about matrices and they say the given metric is a square metric, so what they simply mean by that the number of rows are equal to the number of columns in a given metric. Okay, and we call such metric a square matrices. All right. Okay, now obviously you guys must be wondering what other operations that we can define. I mean, well, in the number system we know we can add 2 numbers, right? We can subtract 2 numbers, we can divide 2 numbers, we can multiply 2 numbers, and there's more operations, but you guys just used to this, guys, right? Now, let's see what sort of similar thing we can do here in a matrices, right? So what I'm going to define for you guys here, addition of 2 matrices, right? How to add 2 matrices, addition of matrices. So it says we can add 2 matrices, right? So first of all, the first condition, in order to define the addition between 2 matrices, let's just see if I say given metric A and B, okay? In order for you to define the addition between 2 matrices, the first thing you want to do, the first thing you want to check is that they are both, first of all, they have a square, is a square matrix, so number 1, condition number 1. Both A and B are square matrix. What I mean by square matrix, guys, if you recall from our definition, a square metric is a metric that has the same number of rows equals to the number of columns, right? And the second condition you want to check when you want to add 2 matrices is that the dimension of metric A must be the same as the dimension of metric B. Okay, if they don't have the same dimension, then we cannot add a metric. All right, let's look at a quick example. Let's see if I give you metric A, 1, 2, 2, 1. If I give you metric B, 3, 2, 1, 4. Okay. And now my question is, I want you guys to perform A plus B. In other words, add these 2 matrices, right? Before I show you guys how to add these 2 matrices, let us first check if condition 1 and condition 2 is in place, right? Okay, what is condition 1? The condition 1 says that both A and B have to be a square metric, right? Or what is a square metric? A square metric is a metric that has the same number of rows and columns. So look at this. In this metric A, the number of columns is equal to number of rows. And the dimension of A, I'm just going to write here, the dimension of A is a 2 by 2, right? And the dimension of B is also a 2 by 2. So the first condition is check. Both of the matrices are square metric because they have the same number of rows equals to the number of columns. And then condition number 2, it says they must have the same dimensions. As you guys can see, both of them have the same order or the same dimension. And now, therefore, now we are good to add these 2 matrices, right? Now the question is though, how do we add the matrices, right? How do we add these 2 guys? So this is what we're going to do. The order of A plus B is not going to change. In other words, it will still be a 2 by 2 matrix, right? So the dimension of A plus B is still the same as the original matrices A and B, okay? So keep in mind that the dimension not going to change. Whenever you're adding two matrices, the dimension of A plus B will be the same as the given matrix A and B, okay? The dimension not going to change. The way we add this two matrices, guys, is that we do it entry-wise, right? We take the first entry from this matrix A, and we add this number to the first entry of your second matrix. So we add these two numbers, right? Okay, now let's see. I'm sure you guys know how to add these two numbers, right? What is 1 plus 3, guys? It's a 4. So therefore, we're going to have a 4 here, okay? Let us look at the now second entry now. The second entry here is 2. Now we're going to add this, guys, with that entry here. It goes entry-wise, okay? So now here, in other words, you take, if you took the first row, second column entry, then you must do the same thing from here as well. So it will be 2 plus 2, which is also 4. And then now we do this guy with that. So what is 2 plus 1? It's 3. And now finally we do this 1 by 4, which is 5. So this is how you define addition between two matrices. And let us just look at, due to the time limit, let's just look at one last example. And then I'll say I'll be done for the day, okay? Okay, let's just look at that quickly as well. As we recall, the dimension of A plus B is the same as the dimension of A, which is equals to the dimension of B. Let's do a quick example here. 1, 2, 3, 4, 5, minus 6. B 2, 0, 1, minus 2, 0, minus 3. Okay, and now if I ask you guys, A plus B, guys. Now the question is, remember, in order for you to add two matrices, before you apply to, you need to check always whether the given matrix is a square matrix or not, right? So let us look at that. I think so I did a mistake in a square metric definition of a sum. Yeah, sorry. When you look at the summation, it not necessarily has to be a square metric, right? We can still add them component wise. I was confusing myself with the multiplication. So this condition is not a must. The condition that is a must is that the dimension has to be the same, okay? So whenever we're adding two matrices, the dimensions of two matrices has to be the same. Sorry for that. Okay, not the square metric, right? It's not necessarily to be square metric. So now, let's look at this. When we're doing this A plus B, guys, what is the dimension of A here? The dimension of A is equals to 2 by 3, am I right? And also the dimension of B also here is equals to 2 by 3, okay? And as I say, therefore, the dimension of A plus B must be equal to that. So it means that we should have 2 rows and then 3 columns like this, okay? It has to have 2 rows and 3 columns. Now let us do that. And as I said, it has to do entry-wise. So it would be 1 plus 2. What is 1 plus 2? That is 3. So we put a 3 there. Then now, since we're looking at this now, so we take this guy and we add it to this entry here. So what is 2 plus 0? It's 2. Then we take this guy and we add it with the corresponding entry that side of matrix B. So what is 3 plus 1? That is 4. And then we have 4 minus 3. Sorry for that, guys. We have 4 minus 3, which is 1. Then we have 5 and plus 0, which is 5. And then we have minus 6 plus minus 3, which is going to give you a minus 9. So that's how you define the addition and a subtraction. The subtraction definition is almost similar to the addition metric, and a multiplication is a bit different. Okay. Obviously, due to the time limit, I couldn't go over everything, so that's all from my side. However, I would like to emphasize is that the matrices have a nice applications in computer science, in cryptography, in economics, in robotics, in four industrial revolutions. It has a very good applications. So if you look at the computer graphics, right? So the computer, the pixels that you see, right? So what it happens is that when you're doing when they're making this thing, the rows in the column of the pixel will represent the same rows and the columns that we know of a metric, and the entries inside the metric represent the color of a pixel. Okay, so let's say if you have a pixel of size 2 by 3, in other words, it will have 2 rows, okay, and it will have 3 columns. Sorry, it will have 3 columns like this. And now, so in the pixel, what happens is that the rows and the columns of a pixel is the same rows and the columns of a metric. However, the entries of a pixel that you would see or inside the metric would represent the color of that pixel. And when I talk about pixel is about this graphics, you know, the photos that we take, the way your phone takes these photos. What it does is that it recognizes your faces, and it assigns these values to your faces, the corners of your head, the corners of your noses, and that it assigns those values, and it creates this nice image using a pixels, which in the background the pixel uses this concept of matrices to digest or to take this picture. And that is one of the application of matrices. There's many more. Obviously, you're going to learn more about matrices in your first and second year. So that's all from my side. Thank you so much for your time. And I thank the organization committee for giving me this opportunity once again. Have a great evening. Any questions? Anyone have any questions?
We have one question on Facebook.
Okay, sure. What is it? Can you please read it for me?
Okay. Should avoid when solving matrix.
Sorry, come again.
Any common mistakes that students should avoid when solving matrix?
Oh, yes. Oh, yeah, it's actually a nice question. It's actually a nice question. Yes. So whenever you're trying to, so first thing is that when you look at the system of equations, right, you must able to the first step, you should be able to write an argumented metric that I showed you guys. And then, as I said, in order to get the solutions X, Y, Z, in order to find those values that satisfy those equations simultaneously, there are 3 operations which we call an elementary operations, which we perform in matrices, and which I haven't showed you guys what are those operations, right? I can tell you guys it's about when you interchange the rows, you can multiply a row by a number, provided that it's not a 0, and then you can add 2 rows by multiplying by a number, or like you multiply 1 row by a number and then add it to a second row. And when you do this thing, when you're solving for those matrices, in order to get those values X, Y, Z, you need to be very careful when you're doing your additions and your subtractions in your mind. Because now imagine you just say, okay, 2 times 3 plus 4, and sometimes you do a mistake, right? As we also saw now about doing addition between 2 matrices. And as you guys can see, when we have to do that component-wise, right? We need to do that entry-wise. So when you rush, sometimes you do a mistake. So you need to just be careful, just double check your work and take your time. In the first glance, it will take you, I mean, trust me, when I was introduced to this topic in my undergrad, it took me about 1-2 weeks just to understand what this matrix is all about. And I'm really glad that this time you guys getting introduced to this concept of matrices far before then you come to university, which is nice. Because when we got introduced, it took me about 2 weeks to just get the whole of this matrices. Once you understand the matrices, how it works, then it's really nice. You're gonna do a lot of more operations that is gonna go on, and you'll enjoy this topic. You'll enjoy more than calculus. I can guarantee on that. I hope I answered the question. Any other questions? Any more questions? All right, so if there are no questions, then yeah, we can call it off. Thank you so much, everyone, for joining me. And it was a lovely session. I really enjoyed it. Have a lovely day all. Bye-bye.